Hi everyone, we will continue with our seventh question of the exam style questions. This question is a little lengthy and has different parts, but all the topics are the topics that we have already practiced in our previous exercises of the chapter. Taking a start with the first part of the question, we are asked to use a factor tree to express 400 as product of prime factors. So we have already practiced this in our previous exercises. How do we do that? We write this 400 as product of two factors. So 2 multiplied by 200 is equal to 400. The number that is prime, that is being encircled, and the number that is composite, it is split further into two factors. And again, the same procedure has been implemented. The one that is a prime, that is encircled, and the composite number is split further. So 2 multiplied by 200 is equal to 400. Then 2 multiplied by 100 is equal to 200. Then 2 multiplied by 50 is equal to 100. 50 being the composite, it is split further. 2 multiplied by 25 is equal to 50. 25 being the composite is split into two primes, that is 5 multiplied by 5, and here is where we stop our factorization. So from this, the factors that we have received for 400 are 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 5 multiplied by 5. All the circled primes that you see in here in this tree diagram, they are expressed as product of prime factors in here, or we can write them as 2 raised to the power of 4 multiplied by 5 raised to the power of 2. Done with the first part, moving to the next one. Use the division method to express 1080 as product of prime factors. So in here, this is how we do the division. We make a table and we write the number that is to be divided, and we take the smallest prime possible and check if it's divisible. So first with 2, we start dividing it from left hand side. So 2 multiplied by 5 is equal to 10. 2 multiplied by 4 is equal to 8, and 2 multiplied by 0 is equal to 0, or we can say 2 multiplied by 40 is equal to 80. Now in here, 1080 was completely divisible by 2 when 2 is multiplied by 540. Now this 540, we will divide it further. Again, we will give it a try with the same prime number 2 and see if it's completely divisible. So 2 multiplied by 2 is equal to 4. In here we are having 5, so that 1 would be lended to 4, and 4 will become 14. So 2 multiplied by 2 is equal to 4. That 1 lended to 4 becomes 14. And 2 multiplied by 7 is equal to 14. Or 2 multiplied by 7 is equal to 14. And then 2 multiplied by 0 is equal to 0. This way we were able to divide 540 by 2 when 2 is multiplied by 270. Again, we try to divide 270 by 2. So 2 multiplied by 1 is equal to 2. 2 multiplied by 3 is equal to 6. In here we are having 7, so that 1 is being lended to the 0, and the 0 becomes 10. And then if we multiply 2 by 5, we get 10. So this way we were able to divide 270 by 2 completely when 2 is multiplied by 135. This 135 cannot be further divided by 2, so we move to the next prime number, which is 3. So 3 multiplied by 4 is equal to 12. We cannot consider the first digit only because it's smaller than 3. Therefore we consider the first two numbers. It makes it 13. So 3 multiplied by 4 is equal to 12. Since it's 13, 1 is being lended to 5, and 5 becomes 15. So 3 multiplied by 4 is equal to 12, and 3 multiplied by 5 is equal to 15. Or we can simply say 3 multiplied by 45 is equal to 135. Since it's division, I'm trying to make a sense of it, how the division is being done. Then we have 45, so how do we divide it? 3 multiplied by 1 is equal to 3. It is 4. 1 is being lended to 5. And 3 multiplied by 5 is equal to 15. So 3, or we can say 3 multiplied by 15 is equal to 45. Then 3 multiplied by 5 is equal to 15. When we get 5, this can no longer be divided by 3, so we move to the next prime number, which is 5. So 5 multiplied by 1 is equal to 5. So the factors that we have received, it is 2, 2, 2, 3, 3, 3, 5. If we express these factors as product of prime factors, it would be expressed as 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 3 multiplied by 5, or we can express it as 2 raised to the power of 3, 3 raised to the power of 3 multiplied by 5 raised to the power of 1. So with this, we are done with the first two parts of the question. The third part of the question is utilizing these prime product of prime factors for these two numbers and find further information about these two numbers. For example, we are asked in here, use your answer to find the LCM of 400 and 1080. So using these product of prime factors for these two numbers, we have to find the LCM of these two numbers. So again, we express the product of prime factors for 400 and then for 1080. And then for LCM, what do we do? The rule is, just as we have mentioned in here, we express the product of prime factor for each number. After doing that, we choose the primes that appear in either number, and we choose the highest power of each prime. So in here, the highest power of the prime 2 is 4, because in here it's 3, in here it's 4. So we will consider the highest power. We will write this. Then 3, although missing in 400, it is present in 1080. So this is a very important point, that we list every prime that appears in either of the either number. So even if this 3 is missing in 400, this prime, it is present in 1080, so we consider this, we write this, or we list it. So 3 has the highest power of 3 because it's missing in 400, so we write it. 2 raised to the power of 4 multiplied by 3 raised to the power of 3, and 5 is present. The prime of 5 is, the factor of 5 is present in both of them, but the highest power is with that of 400, 5 raised to the power of 2, so we take the highest power. So we take the highest power of each prime appearing in both numbers, and we list every prime that appears in either number, either it's in 400 or in 1080. If it's there, we are going to enlist it, and then we multiply it as we have shown in here. 2 raised to the power of 4 is equal to 16, 3 raised to the power of 3 is equal to 27, and 5 raised to the power of 2 is equal to 25. Then multiplied together, we get 10,800. So the lowest common multiple between 400 and 1080 is 10,800, or the multiple that is common between these two numbers, which is the lowest one, which is the lowest multiple, is 10,800. With that being done, we move to the next part that asks us to find the HCF of 400 and 1080. So again, we use the product of prime factors, and in here, while going for the highest common factor, we take the lowest power of common primes. In here, the lowest power of 2 factor 2 is 3. The lowest the lowest power of factor 5 is 5 raised to the power of 1. One thing that is different than the LCM is that we take the lowest power of common primes, the primes that are common in both the numbers. Since 3 is missing in here in 400, so we do not consider it. It is something different than that of the LCM, which we practiced just now. So the lowest common of prime 2 is 3. The lowest power of prime 5 is 1, so we consider these two. Multiplication takes place. 2 raised to the power of 3 is equal to 8, and 5 multiplied by 8 is equal to 40. So the highest common factor of 400 and 1080 is 40. Next, we come to the square root of 400 we are given, and we have to find what the square root of 400 is equal to. So again, we will be utilizing the product of prime factors for 400. We write these factors as factor pairs. For example, this is one pair, this is another, and this is the third one. From each pair we take one factor. So from this we take factor or 1 prime, 2 from this prime 2 again, and from this we take 5. We multiply them. 2 multiplied by 2 is equal to 4. 4 multiplied by 5 is equal to 20. So square root of 400 is equal to 20. The last part of this question is we are asked whether 1080 is a cube number or not, and what procedure or method will we use in order to tell how can we tell if it's a cube number or not. So again, utilizing the product of prime factors, and since it is not a cube number, therefore we can say that it is 1080. If it's the primes are not multiple of 3 or divisible by 3, therefore we can say that it is not a cube number. So we check the prime factorization. If any exponent is not divisible by 3 or a multiple of 3, then we say that the number is not a cube. So again, using the product of prime factors, we identify if a number is a cube number or a square number. Among the primes, the 5 is the prime that has the exponent is not a multiple of 3 or divisible by 3. Therefore, based on this, if it had 5 raised to the power of 3, we would have had said that it is a cube number. So any exponent, prime missing the exponent that is divisible by 3 or multiple of 3 makes it ineligible to be a cube number. So in here we check the prime factors, we check their exponents, and the condition is if it's multiple of 3 or divisible by 3. If this condition is not met, we can say that the number is not a cube. So this is all for this question. I hope it is all clear. Happy learning.